So who can I check in with for chapter 21, number 54? 54, chapter 21. Who can I check in with? There's 8 of you. Somebody. Okay, all right. So for 54, for number 54, we've got 2 wires. We've got this segment of wire, I'm going to put this over here, segment of wire right here that has 12 amps. And then down below, we have a loop of wire which has 25 amps. So we've got this loop of wire down here which has 25 amps. We've got some current going in a loop down there. Okay? And again, the key has a derived equation that they didn't show where it came from. You can't start where the key started. Okay, not for the AP test. We will end up probably deriving that as we go here. Grab a better expo. There we go. All right. And it tells us to review something. We're not going to do that. Okay. So I've got that, and all that's it. We got some distances on here as well. So we've got 0.11 meters is the distance from here to here. This is not to scale. So we've got 0.11 meters from one wire to the top of the other wire, and then 0.15 meters from here to here. So 0.15 meters from there to there. And I think that's all they gave you. And they said determine the magnitude of the net force that acts on the loop. There are lots of variations on this question, but it's very likely that you'll be asked to do something like this at some point on either directions or magnitudes for multiple choice or free response. Yes?
They also give you 0.5.
Oh, they gave me something else, 0.5? Oh yeah, we need the length of the wire. Thank you. So the lengths of the wires are 0.5 or 0.05? 0.5. All right. None of this is to scale at all. Are we okay with that? And it's not in the book either. It's not to scale in the book either. So 0.5, yeah, obviously. Okay. All right. So our 0.5 meters are distance from here to here and here to here. So we have 2 wires, okay? To keep things straight, I'm going to go ahead and call this wire 1 and call this whole thing down here or I1. I'm going to go ahead and say that we have a current here. We'll call this I1, and I'm going to call this current I2. And generally, I'll refer to this as wire 1, wire 2, but wire 2 has 4 segments. Are you okay with? Okay, all right. And we're trying to figure out the force on this loop of wire. So now we got to figure out all the directions of the forces first, okay? In my opinion, that's how I'm going to do it. And then we'll deal with the magnitudes, okay? So we need to use our right-hand rules. So to figure out the force on this loop, remember, this loop cannot exert forces on itself. So what's the magnetic field that will be affecting this or exerting forces on this? The magnetic field created by my 12 amp current. Is that idea okay? All right, and what's the direction of that magnetic field down here? It's into the board. Right-hand rule 2, into the board. Is that okay?
Yeah.
So I've got a magnetic field down here that is, I'm going to put it off to the side, but into the board, into the board, into the board. So let's get the direction of the forces first, okay? So I'm going to have a little second picture here. This is for that loop, okay? And let's get the direction of the force acting on this guy. So for forces, I'm using, is that okay for right-hand rule 2? So everywhere down here in the plane of the board, it's in. It'll get weaker as we go, but it's in everywhere. Yes? Okay. All right. So now to get the direction of the force, I'm going to apply right-hand rule 1. So I've got current going to the right and my magnetic field in. So on this top wire, my force will be up. Is that okay? All right. So I'm going to have force up. I'm just going to call it F and not label it right now. We're just trying to get an idea what's going on. Okay? Now, for the one over here, same idea, magnetic field in, except current going down. I'm going to get a force to the right. Is that okay? All right, so I'm going to have a force to the right on that segment. Some force to the right, not labeling anything on here yet. We don't really need it yet, okay? And then current going up, magnetic field in, I have a force to the left. Before I move on to the bottom part, this left and right part, there's a force on this part, this part, this part, this part, this part, this part, all the way down, okay? And the force here is small. The force here is large. The force here is smaller because we're getting further away from the thing that's making the B field. Is that idea okay? Yeah. But we have some symmetry. For every little bit we have here, we have a little bit over here going the other way in terms of force. So what will these two add up to? 0. Is that okay? Yeah. I haven't done anything with formulas yet, but that's how that would work out. So I don't need to worry about these two from a summation standpoint because they'll add up to 0. Is that okay with everybody else? Okay, everybody else? Okay, so now the bottom wire, or the bottom segment of this wire, magnetic field again going in, we get a force going down. And now this one I'm going to go ahead and draw smaller than that one because we are further away from the thing making the magnetic field, so we're going to have a weaker force on this segment of wire. So we are going to get a net force between these two. Is that okay? All right. So these guys we don't have to worry about, but these two we do. So I'm just going to call this force on segment A and force on segment B. So I need to find those two things and subtract them. Are you okay with where we're headed?
Yes.
Anybody else have any questions on where we're headed before? I'm going to look for, I'll call up positive. So I'm going to look for FA minus FB. That's what I'm trying to figure out now if I've drawn this little extra picture, FA minus FB. Now the question is, how the heck do we get that? Okay, so this is where your equation sheet comes in handy, okay, and some familiarity with what equations can you use. So I'm going to try to use the exact same ones that are on here, and they've got, they do have fib on here, so I'm going to go ahead and write that. They've written it as FM equals, oh, they got it a couple different ways. They have IL cross B or IL sine theta B. What is our angle between our currents and our B fields here? Anybody? 90, no matter what you're looking at. What's the sine of 90? 1. So I'm not going to write the sine part. Is everybody okay with that? They're already perpendicular. We're already at a maximum. Okay? But I'll write F of M will equal I. And then they've got IL. They got a little arrow on there. And then they got a B for an arrow on there. Okay? Really? They put an arrow on the L? Okay, sure, whatever. Okay? But I would typically just write that as F equals ILB. Is that okay? But that's what it'll look like on there minus the sine theta. They have some absolute values on there as well. They've got some absolute values on that. And they have some absolute values on that. And then there's a sine theta. Okay? All right. So I'm going to figure out this force of A applying that equation. So I'll have the current. And I got to be careful. Okay? This is the current that's running through this wire. This is why the notation becomes so important, okay? So I'm going to have my I2, okay, times my length of that wire, which is 0.5 meters. But I do want to derive the equation they have in the key, so I'm going to leave this a little bit more generic right now, and we'll just call it L. But my L is 0.5. Is that okay? That's the length of that wire, okay? And I'm going to make it a little bit less generic. I'm going to call this L2. And I'm going to put up here that we have an L1. But in reality, L1 and L2 are the same. Is everybody else okay with that? I'm doing this so that we can see where that useful equation comes from. But the L's are the same. Okay? So I'm going to go ahead and write that this is the L2, the length of that wire that's in the magnetic field created by wire 1. This is the external field that's created by this wire. Okay? It's the whole reason we have a force. This is the current in this wire. This is the length of this wire. Is that okay? All right. Yeah, but now I've used 1s and 2s, so I got A's and B's mixed in here, but yeah, we'll deal with it. All right. Are you okay with my notation still? I probably should call this. No, I'm going to leave it as a 1 because I'm kind of calling that wire 1, wire 2 now. All right, so let's go ahead now and figure out, this is not enough to get the force, okay, because while we have L, right, and we have I2, we do not have the magnetic field created by this wire. So we need another equation, okay? And on your equation sheet, that other one looks like, this is the one with the mu naughts and all that in it. Yep, this is the same way I would write it. So they've got B equals, well, that's not a B. I don't know what that is. B equals mu naught 2 pi and then I over R. Let me see if I got it the exact same way they got it on there. Mu naught 2 pi I over R, yes, and they have those two separated out. Okay, so some constant times the current in the wire times the distance you are from the wire. Now, occasionally people ask, well, why is it an R? Well, think about it. If this is your wire running up and down and you're here, okay, the magnetic field has the same strength as if you're here, if you're here. What are you carving out? A circle, okay? Is that okay? Or you could do the same thing as like, well, you couldn't do a sphere on this one. You're going to be doing a circle around it. Is that okay? All right. So this is, I'm going to apply it now specifically to get this B1. So this B field created by what I'm calling wire 1 will equal mu naught over 2 pi times my current through the wire that's creating the B field. So that's what I'm calling I1. And then R is my distance from here to wherever I want to know the strength of the B field. So in this case, it would be the 0.11 meters for this first one. Is that okay? for right now, I'll leave it as a generic R because I want to apply this more than once. All right, everybody tune in for a moment because some of you may have shown this or may not have. I doubt you did in your head. The combination of this equation and this equation with substitution is where the key started. But that substituted equation does not exist on your equation sheet. So you do need to have the equivalent of this, and then go ahead and show the substitution. On multiple choice, I'm about to do the substitution. On multiple choice, if you remember the proportionality here, what's proportional what, it's fine, obviously, to do whatever to figure out the multiple choice. Okay? So I'm going to go ahead and plug this in here. We're going to get a result specific to this problem, but we can make it more general. So I2, L2, and then I'm going to have mu naught over 2 pi times I1 over R. So if I rewrite this, now this is specific to this FA thing, but I can rewrite this as, when we've got this type of setup, that force is proportional to the currents in the two wires, okay, times the length of one of the wires, and then we would have over R. So this idea that you have the two currents mattering, the length of wire and the distance from the other wire, that should make some sense. That's where they started. Let me make sure. I'm pretty sure that's where they started the key. They had mu naught I1 I2 L over, and then they did some stuff with the 2 pi. Yeah, they did, and then they have D. Yep. So this is where the key started, except they had the mu naught 2 pi stuff in there. Are you okay with? Is everybody okay with this? But you got to show it on free response. You got to show it on free response. Okay. All right. Don't start there on a free response question. Okay. So now let's make this actually figure out what FA is. So I2 is 25 amps. L2 is 0.5 meters. Mu naught is a constant. 2 pi is a constant. My I1 is 12 amps. And for this FA, I am 0.11 meters away. So I'm 0.11 meters away. Is that okay for FA? All right. Now, to make my life algebraically easier, we could go ahead and do FA minus FB because we could factor out a lot of this stuff because a lot of it's going to stay the same. I'm going to do them separately just for clarity because a lot of times you're not going to have, everything be the same distances and stuff up here. But is this okay? All right. So let's go ahead and would somebody mind calculating that number? That's not really doing anything right now. Calculate that number. You've got it? Awesome. Okay. And all right, so we'll come back to that in a minute here. Let's go ahead and apply that same idea to FB. So for FB now, the only thing that's going to change is that instead of 0.11 meters away, this is where the picture comes in handy, I'm 0.26 meters away. Is that okay? So same thing, except replace this with a which one? This one, with a 0.26 meters. Is that all right? Yeah. Oh, and this equation was for a long wire. So this should probably really be continuing on. Did they show that in the picture or not? They did. Yeah, I need to fix my original picture. This continues off in both directions. Is that okay? Because this equation only applies to an infinitely long wire, or long enough that we don't care about any weird stuff happening on the edges. Okay. All right, so I'll go ahead and just write that all out again. So we'll have 25 amps. 25 amps. We'll have the 0.5 meters is my segment of wire again, 0.5 meters. Got the mu naught over 2 pi. And then 12 amps again, that's what's in that other wire, over my distance, which is now 0.26 meters. And again, you could do the FA minus FB and have factored a lot of this stuff out. What'd you get for this number?
8.68 times 10 to the negative.
Times 10 to the negative fifth? All right. Can somebody get this number and then subtract and see if it works out? Just check to see if it works out. Are you okay with the ideas? Okay. So our last step would be doing this up here. That wasn't so bad. I thought that was going to take a lot longer. I'm assuming those of you that are napping are okay, right? You got this.
When you subtract them, it's 5 times 10 to the negative 5.
What?
When you subtract them, it's 5 times 10 to the negative 5.
5 times 10 to the negative fifth?
Yeah.
And, uh-oh, that's not the right answer.
I might have plugged that in.
Okay, something's wrong. Let me get my calculator out.
Oh, yeah, I didn't do the parentheses right.
So this is wrong. Okay. Where's my calculator? You got what here? FB, you got what? 1.15 times 10 to the negative 4. Have you gotten this one yet? No. Divided by 2 divided by times 2.75 times 10 to the negative 5th. 4th. Newtons. All right, and then let's subtract. So 2.75 minus the 1.115, 1.6, and they got 1.5 or close enough now. Yeah. So 1.5, 1.6 times 10 to the negative 4. Did you figure out your order of operations thing?
Yeah, I just forgot.
Or hit enter a lot more in the calculator. Are you okay with all this? Okay. Where'd the wheels fall off? Was it the mixing of the notation with the ones and the twos, or was it not knowing that these two equations applied, or something else?
Yeah, I mean, generally just the whole thing. I just did not feel good about, and then I think I confused the numbers on these, like the 0.26.
Did you get this part figured out though? That these added up to 0, or didn't even consider it?
No, I got that more.
You got this part, okay. So conceptually you're okay, it's just a matter of being able to, what equation applies. Yeah. Yes?
Do we know what forces act on the coil?
Right hand rules. That was it. I had to go through the process and figure it out.
Okay.
So if you have current and you have external magnetic fields, you have forces. The question is there a net force? Then you got to do this kind of thing every time and figure it out. There's no like set thing for sure that's going to happen.
And how come the coil doesn't exert, like it doesn't have a torque acting on it, or no?
It didn't say anything about pivot points. You're asking me from a problem solving standpoint, why did I not think this thing was going to spin or something like that? Well, I didn't know, but once I actually, so if it was free to move in any direction, and I got a force like into the board here and out of the board here, well then this thing would spin.
Okay.
Is that okay? But
So
I
you just
don't.
have to start with right hand rule too.
Yep, you still got to go with the right hand rules and figure it out. But I didn't expect that to happen because there were no pivot points or anything like that. But you don't know for sure until you do it. Because I mean, if you get a similar setup, you might know it for sure. But you got to go through the process. It doesn't take that long. This was like 3 minutes in, and we'd already figured out that we're getting this. Now, if this is real, if this is like stretchy material, this could get bigger, right? If this was free to slide and move, you could get the thing to be bigger. Except, yeah, it would go both directions. Just go more a little bit. It would go more this way than that way. Well, as a net force, but if this was, there's still that force on the segment of wire. That's me treating the segment of wire as a whole. If this was free to move, these would go this way, these would go this way. Is that okay? Okay. All right, I'm gonna go ahead and stop the video.